Hi everybody, we're going to go over how to balance a redox equation. Unlike the equations in Chem 1 where we just counted the number of atoms on both sides, here we're going to be dealing with oxidation and reduction. That's when electrons are transferred in a reaction. Because electrons are transferred, it's going to cause all sorts of complications. The most important thing we're going to have to do is balance charge and electrons, and by doing that we're going to also add waters, and we're going to add H pluses, and sometimes in basic solutions we're going to add OHs. So this is going to be a lot more complicated than the balancing you did in Chem 1. You're going to need this balancing redox equations packet. This goes through all the steps on how to do it. I've summarized those steps in my own version, my own words here. So these are the steps I'm going to be using. The step numbers line up with the other packet. And finally, I'm going to point out that we're going to be doing worksheet 5. And in fact, we're going to go through for our first example, number 9 right here, which is some tellurium oxide and nitrogen reaction. Okay, I've written number 9 on this piece of paper because we want to have a lot of space to work. So the first thing we're going to do is we're going to determine the oxidation states in the reaction. So in our tellurium oxide right here, you notice that the entire tellurium oxide ion has a 2- charge. Right? That's not the charge of the oxygen atom, that's the charge of the entire species here, the entire ion. So in redox chemistry, we pretend that the more electronegative atom gets all the electrons. And so oxygen, we're pretending, gains electrons here, and it gets the same charge that we get as an ionic compound, which is 2-. All right, there are 3 oxygens, and if each of them is 2-, then the whole entire oxide part of this is 6-. All right, tellurium would be 6+ if the whole thing was neutral, but you'll notice that the entire species is 2-, which means there's 2 extra negatives. That means the tellurium part of this is only 4+. And that means that the tellurium ion has a 4+ oxidation state. Over here, nitrogen, oxygen. Oxygen is the more electronegative atom, so oxygen gets a 2- charge, or oxidation state actually. And there's 4 oxygens, so this whole side's 8-. This whole side has to be 8+ because the entire chemical is neutral. And so that 8+ has to be divided over 2 nitrogen atoms, so each of the nitrogen is 4+. Over here, tellurium's an element alone, so it's 0. And over here, nitrate has a -1 charge for the entire ion. Each of the oxygens is 2-. Overall, they're 6-. So the nitrogen has to balance out the 6- enough to leave only a -1. So that means it has to be 5+. So 5+ and 6- is the -1. All right, so 5+. So I've just finished step number 1 here, determine oxidation states. All right, what we'll notice here is that tellurium is going from a 4+ to a 0, which means tellurium is reduced. Literally, its oxidation number goes down. It's gaining electrons. On the other hand, oxygen is 2- everywhere, so oxygen is neither oxidized nor reduced. It's nitrogen that's changing its oxidation state. Nitrogen is going from 4+ to 5+, so N is oxidized. Its oxidation state is going up. It's losing electrons. So essentially what's happening in this reaction is nitrogen's losing electrons to tellurium. All right, to balance this, you can't just count atoms. We actually have to go through and consider every atom and what the charges are. All right, the first step here that we're going to do is we're going to write half reactions. What a half reaction is it's when we write just the reduction part, and we write a reaction for just the reduction part, and we write a reaction for just the oxidation part. So if you run a battery, these two would be going on in different chambers. By doing the two separately, we can consider the oxidation separately from the reduction. This is going to make it a lot easier to balance the equation. So what I'm going to do is I'm going to write a half reaction just for the tellurium reduction part. Right, I need to write the 2 compounds or the 2 species that have tellurium in them. So first is this one, and arrow tellurium as an element. All right, I'm going to keep all the oxidation states just to make this easier on myself. All right, so we have tellurium turning into tellurium. This tellurium is bonded to oxygen, so we have to keep it bonded to the oxygen in the half reaction. So this is called the reduction half reaction. All right, we're also going to write a half reaction for the oxidation. So this is where N2O4 turns into NO3 2 minus. And so I'm going to write all the oxidation states again. And 5 plus N2 minus. And so this is the oxidation half reaction. Okay, that was the step. Now we're going to go on to balance the half reactions. All right, this is going to involve balancing the atoms first, the elements. Then we're going to balance oxygen, then we're going to balance hydrogen. All right, first is we have to balance everything that's not oxygen or hydrogen. So tellurium, there's one tellurium here, there's one tellurium here. All set. But there's two nitrogens here and there's one here. We've got to balance nitrogen by putting a 2 there. All right, nitrogen is balanced. So we balanced all atoms except for oxygen and hydrogen. Now we balance the oxygen. And we're going to do this by adding an H2O. You'll notice that there's 3 oxygens on this side of the reaction for tellurium. We have to have 3 oxygens on this side, and the only way we can do this is we can write plus 3 H2O. All of these reactions are taking place in water, so there's plenty of water around. It's not a big deal to do this. Water is actually involved in the reaction here. All right, so we balance the oxygen. Let's balance the oxygen here. So you'll notice that here there's 4 oxygens. Here there's 6 oxygens, 2 times 3. So we've got to write 2 H2O over here. All right, now we need to balance the hydrogens. Well, I just introduced a bunch of hydrogens here. There's 6 hydrogens on this side, so I got to write 6 hydrogens over here. We're going to write them in the form of H+. This is an acid reaction, an acidic reaction, so it's okay to do this. And then I'm going to write, again, there's 4 hydrogens here, so I'm going to write 4 H+'s here. All right, I just balanced all the atoms. Now I need to balance the charges. And I'm going to balance the charges by adding electrons. All right, what we're going to notice here is there's 6 pluses here, and there's a 2 minus there. And then there's a 0 and a 0 here. So you'll notice that there's 6 positives, 2 negatives. That means this entire side of the reaction is 4 plus. And this entire side of the reaction is 0. That's not charge balance. We need to add electrons to this to balance out the charges. If we have 6 positives over here, we need to also have 6 negatives over here to balance them out. Those are the 6 electrons. Excuse me, 4. 4 positives means 4 negatives. So I'm going to write 4 electrons on this side. Okay. In this equation, we can see that we have water. Water's neutral. We have this. This is neutral. We have this. There's each nitrate is -1. I think that's not supposed to be 2. That's -1. And there's 2 of them, so that's 2 minus, and there's 4 pluses. So this entire side of the reaction here is going to be, let's see, 2 extra pluses. So we need to balance out those 2 extra pluses, and this side's 0. So we need to put 2 negatives to balance out the 2 pluses. Now that's 0, and that's 0. Okay. All right. So by the way, they don't have to be 0 and 0. As long as they're the same charge on both sides, it's fine. And the only way we can do that is by adding electron to the side that's more positive. Okay, we're going to get to step 4 here. It ends up, in the end, we're going to add these 2 reactions back together. And if you notice, there's 4 electrons here, and there's only 2 electrons here. And when we add these 2 reactions up at the end, that's going to be a problem because you can't have leftover electrons. So what we're going to do is we're going to need this reaction to also have 4 electrons. And the way we're going to do that is we're going to take the entire reaction and we're going to multiply it by 2. That'll ensure there's 4 electrons here. But that's also going to affect everything else. Now there's going to be 4 H2Os, there's going to be 2 of these, there's going to be 4 of these, and there's going to be 8 of those. So I'm going to go fix that right now. I'm going to put 4, I'm going to put 2, I'm going to put 4, I'm going to put 8, and I'm going to put 4. Right. And so I already multiplied by 2, so I can take that away now. All right. Now we're going to sum up these reactions. So I'm going to put a big summation bar here, and I'm just going to add these up. All right, just like in earlier times this year, if a species appears on both the left and the right side of the reaction, it means that it's not changing. So here we have 4 electrons here, and we have 4 electrons here. There shouldn't be any electrons at the end of adding these things up, so I'm going to cancel that. You're also going to notice that here there's 6 H pluses, and here there's 8 H pluses. And that partially cancels. So the 6 H pluses cancels the 8 and leaves behind 2. Okay. Waters. You'll notice there's 3 waters here, and there's 4 waters here. Again, that's also going to partially cancel. So 3 waters will cancel 4 and leave behind the 1 water. All right, and I think that canceled everything. So now I'm just going to add it all up. I'm going to put 1 H2O plus the 2 N2O4s plus the TeO3 2 minus makes the 4 NO3 minuses plus the Te plus, what is it, 2 H pluses are left over. And that's the final balanced reaction.